Okay, so let's talk through this problem of 3x e to the negative 0.5x and take a look at how we're going to graph that. So we're going to start with the intercepts. So if we start with the x-intercept, we know that to find the x-intercept, we want to set this function equal to 0 and solve for x. Now, what you have to remember about e's is that e to anything is always strictly greater than 0. So you can never set an e equal to 0 and solve for x because e is always positive. And of course, a negative in front of an e to anything would always be strictly 0, less than 0, sorry. So again, there is no time where an e to anything can ever equal 0. So that's why when you're finding the x-intercept and you look at your two factors, you've got two factors here. We've got one that's 3x and one that's e. The only one that you actually set equal to 0 is the 3x because an e cannot be set equal to 0. So when you set that equal to 0 and solve for x, you get x is equal to 0. So that's why my x-intercept is 0, 0. Now if we do the y-intercept, now we want to plug 0 in for x in the function. So of course you've got this 3x out front. So you're going to have 3 times 0 times e to the 0, but anything times that 0 gives you 0. So my y-intercept is also 0, 0. Now we're going to move into the derivatives in order to find critical values. So let's start with the first derivative. So for my first derivative, I want to treat this as a product rule problem where I'm going to write over here on the side, sorry about that, my first function in my product rule is the 3x. And my second in my product rule is going to be that e to the negative 0.5x. So in the product rule, we want to do first times derivative of second plus second times derivative of first. So let me just do these derivatives so that I can pull from that as I go through and do the problem. So of course the derivative of 3x, so dy dx of 3x is just 3. And if we do the same thing with the e, the derivative of e to the negative 0.5x is, now the rule for derivatives of e's is the first thing I write down is the derivative of the exponent. So the derivative of my exponent is negative 0.5, and then you just repeat the e. So my derivative of e to the negative 0.5x is negative 0.5 e to the negative 0.5x. That's just that rule for doing a derivative of an e. It's the derivative of the exponent times the original e with its original exponent. Okay, so back over here to my derivative, I want my first, which is 3x, times the derivative of the second. So that was this part over here. So I'm going to multiply by negative 0.5 and then my e to the negative 0.5x. And then it's plus the second function, unchanged, times the derivative of the 3x, the derivative of the first, which is just 3. And now what I want to do is factor this so that I can set it equal to 0 and find my critical value. So I want to identify what my greatest common factor is. So just look on the left of the plus sign, on the right of the plus sign, and find what they share in common. So I notice that they share a 3 in common, and they share the e in common. So that means my greatest common factor is going to be the 3 and the e to the negative 0.5x. And behind that, I'm going to write down all of the other things, left of the plus sign and right of the plus sign. So I'm going to divide this out from each side. So if I do that, then on the left side of the plus sign, the 3 will divide out and the e part will divide out, leaving me the negative 0.5 and the x. And on the right-hand side, notice everything divides out. But when I divide anything by itself, I'm left with a 1. So I still have a plus 1 that I have to include there in my derivative. So that is my derivative, and that's what I want to set equal to 0 and solve for x. So now that it's in factored form, I want to set each factor that I can equal to 0 and solve for x. So we don't set a 3 equal to 0 because that wouldn't make any sense. And based on what I said to you up in here, I do not set my e equal to 0 because an e can never equal 0. So the only thing that I'm setting equal to 0 is the negative 0.5x plus 1. So if I subtract 1 from both sides and then divide out the half, I end up with a critical value of 2. So now that we have our critical value, now what we want to do is mark that off on a number line and do some testing around it. So there's my critical value. And now I want to test on either side of that critical value to determine if the function is increasing or decreasing. So on the left, I'll test 0, and on the right, I'll test 3. Now, where I'm testing that is in this factored form of my derivative. That's the easiest one to use. Because remember, my 3 is always positive. My e, since the coefficient is positive, with a positive coefficient, e to anything is always positive. So really all I have to do is test the 0 into that factor, since everything out in front is a positive value. So if I plugged 0 in for x in this factor, I'd get 0 plus 1 is 1. That's positive. So that means that I'm increasing on the on the left of 2. Now we're going to do the same thing with my test value of 3. If I plug 3 into that factor, 3 times negative 0.5 is negative 1.5. So if I add that to 1, it's still going to be a negative value. So now it's decreasing. So that means what we know is for this function, it is increasing from negative infinity to 2, and it is decreasing from 2 to infinity. And based on the shape of my increasing, decreasing, I know that 2 and whatever its y value is a relative max. So to find the y value, I would need to plug that back into the original function. So f of 2 would be 3 times 2, and then e to the negative 0.5 times 2. So that's going to give me a 6 out front, and negative half of 2 would be e to the negative 1. So I'm just going to list my y value here. Oops, I meant to erase that. List my y value here as 6e to the negative 1. And then, of course, when it came time for graphing, I'd want to put that in my calculator to get a decimal approximation for that y value. Oftentimes, when you're asked for the relative max, you may, in MyLabs Plus, only have to list the x value for the max or the min, so just pay attention to the directions on whether you need to find that y value. So that's everything with the first derivative. So now what I want to do is find my second derivative. Okay, so I have refreshed my page here where I've got the original function written at the top and then the derivative that we found, just kind of cleaning out the page so that I have room for my second derivative. So we are now moving to the second derivative, which I again need the product rule. And in this product rule, the 3e to the negative 0.5x will be my first, and this part in my parentheses will be my second. So running through the product rule, my second derivative will be, the first stays the same, and I multiply that by the derivative of the second. So the derivative of this second piece here, the derivative would be negative 0.5, and the derivative of 1 is 0, so that would be the full derivative of that second factor. Plus, now I leave the second factor alone, and I do the derivative of the first. So for the derivative of this first piece, I'm going to move my derivative of my exponent on e out front with that 3. And you can multiply them together. I'm just going to leave them separate right now. So this is just going to be 3 times negative 0.5. And then the exponent stays the same. So the e and its exponent stays the same. So all I did for this piece here was I kept the 3, I moved the derivative of the exponent out front, and then left my e alone. Okay, so now we need to simplify this the same way we simplified the first derivative. So I'm going to first identify what the left-hand side of the plus sign and the right-hand side of the plus side share in common. So if I look for what they share in common, they both have a 3, they both have an e to the negative 0.5x, and they both have a negative 0.5. So that means that my greatest common factor is the 3e to the negative 0.5x and the negative 0.5. That's my greatest common factor. And I want to divide that out from both the left-hand side of the plus sign and the right-hand side. So notice on the the left-hand side of the plus sign, I'm dividing each one of those out. So if everything gets divided out, it leaves me a 1. And on the right-hand side of the plus sign, I'm dividing out these 3 terms, leaving me this part in parentheses here. So it's leaving me a negative 0.5x and the plus 1. And I don't really need those parentheses there. I just kind of did that to emphasize that that's what I have left. Okay, so I want to clean up what's inside this parenthesis, just combine those ones together. And then also out front here, I'm going to go ahead and now multiply that 3 and negative 0.5 together. So my second derivative is going to be 3 times negative 0.5, and I'm going to switch to fractions just because I like fractions better than decimals. But if you want to leave it a decimal, you can. So 3 times negative a half would be negative 3 halves. And then my e. And then inside those brackets, the 1 plus 1 gives me 2, and I still have the minus 0.5x. Okay, so there's my second derivative that I now want to set equal to 0. So now remember, we want to set each factor that contains x equal to 0 if it makes sense to do so. So I am not going to set negative 3 halves equal to 0 because that doesn't make any sense. And now hopefully you're recognizing that I do not set an e equal to 0 because that doesn't make sense since an e can never equal 0. So the only thing that's going to produce a critical value is going to be that factor. So I'm going to set 2 minus 0.5x equal to 0 and solve for x. So if you subtract that 2 and then divide out that negative half, my critical value is 4 for my second derivative. So just like the first derivative, we want to mark that critical value off on a number line and do some testing on the left and on the right. So pick a number to the left of 4, and I always pick 0 when I can because the arithmetic is easy. And pick a number to the right of 4, I'll choose 5. Now, this time when I look at my derivative and I'm thinking about what am I going to get when I plug 0 into that second derivative, am I going to get a positive number or am I going to get a negative number? This time when I look out front here, so if I look out front at this factor here, we know that -3/2 is always going to be negative, and we know that e to a power is always positive. So that factor out front, circled in green, is always going to be negative. Now what we need to figure out, so that negative sign came from there. Now what we need to figure out is what happens when I put 0 into that factor. Will I get a positive or negative result? And if I put 0 in for x, I'm going to get 2, so that's a positive result. And a negative times a positive is a negative, so that portion is going to be concave down. Now we want to do the same thing with the 5. Once again, that part circled in green out front is going to be negative no matter what x I use. But when I put 5 into that factor this time, 2 minus 0.5 times 5 is going to be 2 minus 2.5, which is negative, and two negatives make a positive, so this portion is going to be concave up. So we can claim now that my function is concave up from 4 to infinity, and it is concave down from -infinity to 4. And because the concavity is different on either side of that 4, we know that 4 is an inflection point. And if we need to find the y value, we can plug that 4 back into the original function. So 3 times 4 e to the -0.5 times 4 would give me a 12, an e, and -1/2 of 4 is -2. So for my inflection point, I can say that my inflection point is located, I'm sorry, I don't know where the 2 came from. My inflection point would be located at 4, 12e to the -2. And then I would need my calculator to estimate that value so that I could plot it. So this was a tough example because you had a not so wonderful exponent on the e, and then you also had the product rule involved. But hopefully this helps you out a little bit. I would be more concerned about the polynomials. Make sure that you can do the polynomials well. And then if you understand how to find those critical values for the polynomials, then it makes these tougher ones a little bit easier. But again, feel free to email me if you have questions about this video or anything else.